Hey guys, we're taking a look at the derivatives for log functions today. We're going to talk about some general rules and also how to put together some of the other rules that we've been talking about with taking derivatives. So the first thing we're going to do is this little investigation. And we look at the investigation. We're saying, okay, look at the function y equals the natural log of x. What's its gradient function? Obviously, we know gradient function is just another way of saying what's the derivative function look like. And we're going to start out just by looking at y equals the natural log of x. Go ahead and throw that into your calculator. And when you do, it looks something like that. Now, the second step in this investigation says, describe the change in the slope as x increases. Well, if I have a small value of x, maybe I'm looking here at x equals a half. That has, I missed my point there, but that has a very steep slope. But if I were to choose a point much farther out there, say x equals 5 or 7 or something like that, we would see that the slope of the tangent line is much smaller there. So that should tell us something about what the derivative function should look like. It should start with large values, and then as it increases, it gets smaller and smaller. Now, in step 3 of this investigation, we can actually go through and find some derivative values for different x values. All you have to do there is keep the values, keep the function plugged into y equals, and then hit second, calc, and choose option 6, which says dy dx, and then plug in your different x values. When you do that, you get your dy dx values. When you plug in a quarter, you end up getting the derivative is 4. When you plug in a half, the derivative is 2. When you plug in 1, the derivative is also 1. You get 2, it's a half, and it's a third, a fourth, and a fifth. I would suggest you take the time to go ahead and try that on your own to make sure that you understand how to get those values and to then look at them. Now, what we estimated or what we proposed was going to happen was that as x increased, the slope of the tangent line would decrease. And that's exactly what we see. So step 4 says, do your results confirm what you thought in question 2? Well, yeah, they do. But it goes even further than that. There's a clear relationship between a quarter and 4, between a half and 2, 1 and 1, 2 and a half. There's a relationship that exists there, and we could take that relationship one step further, and we could come in and say that if you have y equals the natural log of x, then the derivative is just 1 over x. The proof underneath here uses the function we referred to, but converting it to exponential form. And then through an application of the chain rule, you can see that you end up getting that 1 over x. So that is the general function for the natural log of x. Its derivative is 1 over x. But what if we have the natural log of a different function? What if we have the natural log of x squared? Oh, sorry, not e squared. What do you have? The natural log of x squared, or the natural log of x plus 3. Well, if we're in that situation, then we have to take a different approach. And this approach, just like it was when we dealt with the exponential function and their derivative, is an application of the chain rule. So we start by just looking at the natural log of u, where u is just whatever that function f of x is. And then we just say, okay, if we're trying to find the derivative of y with respect to x, application of the chain rule says you do dy du times du dx, which makes it pretty simple for us down here. The derivative of the natural log of f of x is f prime of x over f of x. So we see whether we have the simple function natural log of x, which has a derivative of 1 over x, or the natural log of f of x, which is derivative is f prime of x over f of x. You'll notice that in both situations, the natural log part of the equation just goes away. We don't need it anymore. And we're going to take a look at some examples moving forward. But before we look at those examples, we want to make sure that we have in mind some laws of logarithms that are going to help us work with these functions as well. Now, these functions require that a and b are both positive, and n is a real number. But if we have the natural log of a product, that's equal to the sum of the logs. If we have the natural log of a quotient, that's equal to the difference of the logs. And if we have the natural log of some value a to the n, you just take that n and slide it right in front and have n times the natural log of a. Just a review from previous stuff that we've already discussed. Now, let's go ahead and take a look at this natural log of kx. Well, this is more than just the natural log of x. So we want to think back. What did we just say? We said the natural log of f of x is equal to f prime of x over f of x. So when I look at this first function here, what is f of x? F of x is equal to kx. And what, therefore, is f prime of x? Well, it's just k, right? So we can just go ahead and plug into that equation and say it's f prime of x, which is k, over f of x, which is kx. The k's cancel, and you're just left with 1 over x. Now you might be wondering, well, why is it 1 over x? Isn't that just the derivative of the natural log of x? Well, that should make sense as well, because you could take a look at the natural log of kx and break it up into the natural log of k plus the natural log of x, keeping in mind that the natural log of k is a constant, and therefore its derivative is 0. That means the natural log of kx is really the same thing as the natural log of x, which is why they have the same derivative there. With our second example, we have the natural log of 1 minus 3x. So we have 1 minus 3x, that's our f of x. And we can then say f prime of x, just looking at that, that's just negative 3. So we should be able to just plug in again to our rule that we said right here. And in fact, when we do that, we end up having f prime of x, negative 3, over f of x, which is 1 minus 3x. And you could go that one extra step and divide out a negative from the top and bottom and make it 3 over 3x minus 1. The first answer, in my opinion, is just as simplified. Looking at part C here, we have two terms that are being multiplied together. So that should tell us that we're looking at the product rule. Now, the product rule means that we're going to have to look at u. Well, u is just going to be x cubed. And u prime, therefore, is 3x squared. We'll have a v, which is the natural log of x, and a v prime, which, as we've already established, is just 1 over x. So when we go ahead to plug in, we know the product rule is u prime times v plus u times v prime. And when we look at that, we look to see if there's anything that we can pull out, and or simplify, I should say, first. And over here on the right, I have x cubed times 1 over x. That reduces down to x squared. And then I realize that each term has an x squared, so I can pull that out. And what am I left with? I'm left with the 3 times the natural log of x plus 1. So a slightly more simplified version there. Look at those for a minute and make sure that they make sense before you move on to the next slide, which has 2 more examples, not harder necessarily, just involving some more work. When I look at A here, I see that I have the natural log of x times e to the negative x. And the first thing that I'd like to do there, rather than having to deal with the product rule inside there, is I'd like to separate it to make it the natural log of x plus the natural log of e to the negative x. All right. Now, as I look at that there, I see the natural log of x. All right. That's just easy. That's just 1 over x. And when I have the natural log of e to the negative x, I can just take that negative x and move it in front. And when I do that, I just end up getting negative x. Now, I still have the natural log of e, but I know the natural log of e is just 1. So when I look at that, I end up just getting 1 over x minus 1. All right, and you see here a little bit more of an explanation. I can separate the logs, and then I can also take the natural log of e to a, and that's just a. In this case, a equals negative x. We're going to take a look at the second example here, the next slide. And while this next example looks more challenging, it's not really more challenging, it's just longer. We're just going to break it up. So we're going to take a look at the natural log of x squared. And then since we're dividing, we're going to then subtract the natural log of the denominator. And since in the denominator we are multiplying, I'm going to then add those. keeping the whole thing in square brackets there to keep in mind that I'm really subtracting the whole thing. Then I say, all right, well, I have the natural log of x squared. You can just take that 2, slide it in front, and now I have 2 times the natural log of x. That makes life a little bit easier because you know the derivative of the natural log of x is 1 over x. Therefore, 2 times the natural log of x has a derivative of 2 over x. Then I'm going to look at the natural log of x plus 2. Well, I know the x plus 2 part is the f of x. So when I go to find the f prime of x, that's just going to be 1. So I have over here f prime of x over f of x for that part of the derivative. And the same thing is true here in the last part. F of x is x minus 3. So f prime of x is 1. So I can go ahead and plug it in. And a more clean version says dy dx equals 2 over x minus 1 over x plus 2 minus 1 over x minus 3. Now, could you go further and find a common denominator? Of course you could, but that doesn't necessarily show any more understanding of the calculus, which is the real point of what we're doing here anyway. So that's it. We just went through and found some derivative functions for logs. And that's it. We'll come back next time and talk about some more derivatives.